Okay.
Welcome into the room. Anyway, so Dr. Becker's with us tonight and her husband, Hank. Welcome, Margaret. Dr. Becker received her PhD in History of Science from the Johns Hopkins University. Until her retirement, she taught History of Science at the University of California, Irvine. Her research interests include the role of the amateur in the development of 19th century professional astronomy, with the redefining of disciplinary boundaries in the face of new knowledge and new practice, and the role of controversy in shaping the substance and structure of scientific knowledge. Becker is the author of the first scholarly biography of English amateur astronomers, William Huggins. William Huggins. The title of the book is Unraveling Starlight, William and Margaret Huggins and the Rise of the New Astronomy, published by Cambridge in 2011. In January 2015, Unraveling Starlight was awarded the prestigious Donald E. Osterbrook. Did I get that one right?
That's
okay.
Good. Yeah.
Donald E. Osterbrook Book Prize by the History of Astronomy Division of the American Astronomical Society. She is also the editor of Selected Correspondence of William Huggins, 2 volumes, Pickering and Chatto in 2014. So with that, I'd like to invite Dr. Becker up, and we'll get started with her presentation.
Great. Thank you very much, Phyllis. Oh, what a big turnout. Thank you. I'm very, very delighted to be here, and always delighted to share my acquaintance over the last quarter century plus with this delightful couple, William and his wife, Margaret Huggins. Nowadays, we have such an instantaneous grasp of stars, what they're made out of, and nebulae, and so on. When somebody's, well, maybe that's not true across the general population, but this group, I think, if you were to say the word nebula or galaxy or nova, you'd know instantly what it was that was being referred to, and you would understand that there's no big mystery about what stars are made out of nowadays. But I want you to go back there we go. Back to 1806, beginning of the 19th century. Your mother didn't write this poem. This is actually written by a woman named Jane Taylor in 1806. You all know by heart the first verse. You may not know that there are 3 verses. And I think what is wonderful about this poem that Jane Taylor wrote is that it encapsulates the general view of stars, what they were made out of, and what we would ever know about them. So this idea of how I wonder what you are, that was really a total mystery at the beginning of the 19th century. What was its purpose? What was a star's purpose? Well, you show your little light and twinkle, twinkle all the night. Why? Well, for the traveler in the dark, who thanks you for your tiny spark. He could not see which way to go if you did not twinkle so. And that was really the principal structure of the heavens. It was a mapping project. It was placing the stars on the sky, knowing where things were located, because there was just nothing else you could ever know. You could never visit a star, grab a bag of it, the stuff in it, and bring it back to a chemistry laboratory as much as you might like to, and figure out what a star was made out of. Philosophers like Auguste Comte, a French philosopher who had a very strict idea of what it meant to do proper science. In his view, you could only really say something scientific if you could actually hold it in your hands, measure it, and come up with some kind of certain statement about its composition, its size, its shape, and something physical about it. So as far as the heavens were concerned, all you could do was map. This is sort of going slowly between each slide, huh? Okay. To find out what Auguste Comte said next, I'll do a little song and dance here. But basically, he was saying that you could never know anything about its. All right, here we go. Success. All right, where were we? Right. Well, so Auguste Comte said there's just absolutely no way that we could ever know anything about the chemical makeup or the geology of a star. Our positive knowledge with respect to the stars is necessarily limited to their observed geometrical and mechanical behavior. In other words, navigational purposes, mapping, and so on. That's basically what astronomy is limited to. Now, philosophers are one group, but another group that was very concerned with this issue were astronomers as well. And one of the best-known astronomers of that time, Friedrich Wilhelm Bessel, agreed very strongly with that astronomy must lay down the rules for determining the motions of the heavenly bodies as they appear to us from the earth. Everything else that can be learned about the heavenly bodies is not properly of astronomical interest. Now, you notice he's writing this in just before 1850, and he died about that time, and so he didn't live quite long enough to see the major transformation that occurred just within the next decade after his death. And that was all brought about by the introduction of this funny little instrument that was very familiar to chemists and to physicists from the beginning of the 19th century. It's called a spectroscope. But what happened, which was really quite an interesting thing, was that suddenly around the turn of the middle of the 19th century, it became appropriated by some adventurous astronomers. And one of the key figures in that process of transferring the chemical and physical utility of that instrument, the spectroscope, into astronomy and putting it to astronomical use was a fellow named William Huggins. Now, his name is not very familiar to most modern individuals. His name has sort of gotten lost in the sands of time because he was an amateur astronomer, and much that he set into motion soon became superseded by the professional community. You needed a graduate degree in order to pursue the kind of science that he started out. But he was, like many of you here, an amateur astronomer, self-taught. He had very little formal education, and his contributions, however, were that he was the very first person on Earth to look at the light of a nebula with a spectroscope to see what its spectrum looked like. He was the very first person on Earth to look at a nova with a spectroscope. And one of his greatest contributions, I think, was that he was the first to attempt to apply Doppler's principle to determine the motion in the line of sight of a star or a celestial body. And he did this all in his home observatory without any formal education. Now, in 1875, he married Margaret Lindsay Huggins, and together the two of them collaborated on many groundbreaking research efforts, and you can see a list of some of them here. Until his death in 1910, they worked collaboratively together as partners. And some of these things we'll talk a bit about this evening to give you a better idea of the details of these things. Now, when William Huggins looked back on how it was that he got interested in this spectroscope business, he wrote that he was just sort of feeling a little itchy. He was a little dissatisfied, as he explained it, with the routine character of ordinary astronomical work. And he was just kind of fishing around for something, some better way to apply himself and to direct his career. And so it was just about that time, 1862 in fact, that he heard about the work of Gustav Kirchhoff with the spectroscope, applying it to the light of the sun. And this is probably the most famous quote from this essay that he wrote, and it has actually influenced a number of practicing astronomers today. They felt very enthusiastic and wanted to, contribute in a similar way. The news was to me like the coming upon a spring of water in a dry and thirsty land. Here at last presented itself the very order of work for which in an indefinite way I was looking, namely, to extend Kirchhoff's novel methods of research upon the sun and the other heavenly bodies. Now you notice the date here is 1897. This is some 35 years after the fact. So he's got a long view of this and the kind of effort that he can already see the fruits of his initial efforts. And so when he's talking about this, he's talking about it with a rather long distant view. And it was from this little excerpt I just read is from a popular essay that he wrote for a magazine of the day, 19th Century. It was published in a very special edition of that magazine, one that was devoted to the Jubilee year of Queen Victoria. So many people purchased copies of this, and it was really widely read. In it, he presents his life and the development of what would become known as astrophysics as a kind of a symbiotic process. The two kind of grew and worked and developed together, each one feeding on the other. And every step that he took, it's like step A, and then, well, obviously I got to go to step B, and then step C. It's all a very nice, neat, linear path that he traces out. All of the questions that he talks about, that he looked into, are things that he found satisfactory answers for and things that he received quite a bit of acclaim for. This essay has served as the basis for most of the biographies that have been written about William Huggins. And for that reason, there is this sort of idea that this is basically all that there is to the story. The thing that's really true, though, is the more I looked into it, starting some quarter century ago, when I started looking into the life and work of William Huggins, I found that actually the story itself is a lot more complicated and it's a lot more interesting. There are a lot of failures involved in the course of his life. As you can look back on your own career, why did you choose to do X as opposed to Y? Why did you move to this city and find employment there instead of on the other side of the country? A lot of these things, looking back on it, it seems very obvious why you did things. At the time when you're making up your mind, you're not sure exactly what the future is going to be like, and it's a little iffier. Well, all of those ifs and all of those question marks are missing from this essay. And what I want to do, and what I've tried to do in my biography of Huggins, is to restore some of those questions, restore some of that fabric, that texture to his life. All right. And here we come to another end of the space bar. Oh, okay. Okay, the other thing worked before. All right. First of all, William Huggins was the son of a silk merchant in the center city of London, right on Grace Church Street, which is Grace Church Street. If you follow it down, oops, is it going to just go? Oh. If you just follow it down to the bottom, past the bottom corner, you'll get to the London Bridge, where it crosses the Thames. He's very close to the Tower of London, which you can see over in the corner there. And so he ran a very successful silk business in the center city of London. That's where Huggins grew up, and that's where he got actually some of his very first taste of what it was like to use optical instruments. His father, being a silk merchant, would have had little optical instruments to count the threads and so on. And by the time he was about 18 years old, his parents had already purchased him his own microscope, and he bought his own very first small telescope. When he was in his late 20s, he became much more interested in sort of dabbling in a variety of sciences. He joined the Microscopical Society. He bought a 5-inch telescope for himself when he was in his mid-20s. And in 1854, he actually became a member of the Royal Astronomical Society. So he's beginning to commit himself to research as an amateur contributor. Now, I want to make sure you understand that in the 19th century, the word amateur isn't a disparaging term. Amateur actually is, it's amateur. It's somebody who loves what they do. They're not paid to do it. They do it because they love it. And in England in particular, there are almost very few. George Airy was one paid scientist of the day, and that was about it in the country of England. And in fact, if you wanted to do science, you paid for it yourself. You used your own money to make it possible to do your work. When around 1855, after William became much more enthused about his astronomy and his parents were aging, it was hard for them to keep up with the business. They sold the business in downtown London and moved to a suburb. Well, it's not exactly a suburb anymore. It's actually very well contained within the major metropolitan area of London now. But in those days, it was actually a very sparsely populated, up-and-coming area where new houses were being still built. And he had a nice southern view out the back of his house. He had a okay, spacebar. There. Oh, I want to go back one. Wait. I'm sorry. It's not doing what I'm. There we go. Okay. At 90 Upper Tulse Hill Road, that little orange-colored rectangle, it's about a 1-acre property. It's a huge property. He had a big garden in the back, and he set up his telescopic equipment there. He actually had an observatory constructed that was attached to his house, so he didn't have to go outside any longer to house his instruments. This is a picture of it after it had been a bit expanded in the 1870s. And he began keeping a regular notebook. He got a bound notebook, and what enthusiasm! Can you imagine this? Here he's got this is a verse from Genesis. Some of you may know the story of Abraham getting worried. He's getting to be an old man. He's afraid he's not going to have any children, and he goes out in the night and he says, "So God, what's up with this? When, I'm not going to have any kids." And he says, "Well, if you want to know how many children you're going to have, just count the stars." And that's what this little verse is, written in Hebrew by someone who hasn't been to school. He's obviously been trained by a tutor in some of the languages. He's got a Greek word here, phenomena, and in Latin, he's describing things that have been seen through the telescope of William Huggins. And underneath that is another little Latin phrase, and that is the motto of the Royal Astronomical Society. And it basically, loosely translated, it means, if it twinkles, count it. This guy, this is his very first observatory notebook. He's just so excited to get started. All right. Oops. It's interesting. I'm not sure. Okay. Well, bear with me here. This is his very first entry in his notebook. He happened to be starting out at a time when Mars was at opposition, and so he's all set to make his observations here. He's even got a little circle drawn in. But he's got this little extra circle there. He's obviously planning to make another observation, as we all are. and didn't ever get to it. His next observations are of a lunar eclipse in 1856, and then an occultation of Jupiter. These are all his own drawings in his notebook. Now, and like all of us, you need a mentor if you have no training in astronomy or how to use these darn instruments like these computers and so on. You need some assistance from somebody who is really quite skilled, and he got that assistance and that mentorship from a fellow in the Royal Astronomical Society whom he met at a British Association for the Advancement of Science meeting, William Rudder Dawes. Some of you may have heard of Dawes because he was a really skilled binary star observer. They called him Eagle Eye Dawes, actually. Dawes was helpful to Huggins in many respects, just for observational technique and so on, and learning to keep a notebook and how to do successive observations instead of just kind of scouting the sky for anything at willy-nilly. He taught Huggins how to go about making specific research-oriented observations, but he also sold him a wonderful objective lens made by Alvin Clark in the United States. It was an 8-inch lens that he sold to Huggins at for what he had paid for it, which was 200 pounds. And Huggins actually had commissioned a telescope to be built. It's not this. This is a telescope that is actually a Clark telescope, but it is not the one that went originally with this lens. It's in the Cincinnati. If you're ever in Cincinnati, go see their little astronomy club's observatory out in the country, and you'll have a chance maybe even to look through this telescope. There's a very interesting story involved with their acquisition of this particular lens, which for some future meeting I'll share with you. It involves theft and reclamation, actually. With this telescope, this new telescope that he got from the new telescope he had built with the lens from Dawes, Huggins continued his viewing efforts on all sorts of different projects. Now you'll notice this brings us down to around 1860, which was the date that many of you will. So 1860 is when two German scientists, Robert Bunsen, the chemist, and his colleague Gustav Kirchhoff, a physicist, announced that they had actually been using their spectroscope to make some rather astonishing discoveries. And in fact, they published a paper in which they announced that once and for all they had solved this great mystery. What is the source of these dark lines that Joseph Fraunhofer discovered that cross the solar spectrum? These were observed in 1820. Fraunhofer had no idea what caused them. He thought they were rather interesting, and he wrote about them in a very lengthy paper. But for several decades, this remained a complete mystery until Bunsen and Kirchhoff discovered that, in fact, these lines are exactly in the same exact spots as lines seen in the spectra of terrestrial elements. When you start to burn them in a flame, if you look at them through the spectroscope, you will see bright lines in places where these dark lines cross the solar spectrum. So their suggestion was that what this means is that we can just look at these dark lines and use them like a code to sort of figure out what the sun is actually made out of. And the sun is not made out of mysterious stuff that's different from earthly things. It's actually made out of exactly the same stuff. Now, a student of Bunsen's was an Englishman whose name was Henry Roscoe. And Henry Roscoe had finished his work with Bunsen and had come back to teach in England. And he was one of the very first in England to hear about this news. They didn't have email in those days. It might surprise you to know that email is not something that goes back to the 19th century, but he did hear about it through reading a journal. And then later, He heard about it directly from Bunsen himself in a nice letter, and he immediately sends this information off to his friend George Gabriel Stokes. He's so excited that what we have here then is a kind of a mechanism for doing qualitative analysis that will allow us to determine, just if we look at the light of an object, we can determine exactly what its chemical nature is. So Roscoe began giving a number of lectures around London about this wonderful discovery. And one of the individuals who heard one of Roscoe's lectures was a fellow named Warren de la Rue. De la Rue was actually an amateur astronomer who became so excited by what he heard. He dabbled in chemistry and a number of other things as well. And he wrote in this article in the Chemical News, if we were to go to the sun and to bring away some portions of it and analyze them in our laboratories, we could not examine them more accurately than we can by this new mode of spectrum analysis. In other words, Auguste Comte and his philosophy of science, we can now answer all of his questions. We don't have to go to the sun directly. We can bring it to us through its light. It is not an uncommon thing for a physicist to tread upon the ground which a chemist thinks belongs to him, and for the chemist to tread upon the ground of the physicist. Now we have the chemist occupying the ground of the astronomer. And if the astronomer wants to know something of the constituents of the heavenly bodies, he must come to the chemist. Well, the one thing that de la Rue hadn't counted upon is that astronomers might want to just do this by themselves. One way that this happened was that another chemist in London, William Allen Miller, was also giving lectures on this wonderful new development. And an attendee at one of Miller's lectures was none other than William Huggins. William Huggins became so enthused about what he heard, he writes, a sudden impulse seized me to suggest to my neighbor, William Allen Miller, to join me in the attempt I was about to make to apply Kirchhoff's methods to the stars. And in fact, they were indeed neighbors. You see 90 Tulse Hill Road right here. That's William Huggins's house. This is where William Allen Miller lived. And the two of them apparently shared a carriage ride home after William Allen Miller's lecture. Huggins, got him finally to agree to come over on the first fine night, and they would begin this observing project, applying what Miller knew about chemistry to what Huggins knew about astronomy. And they were going to figure out some way to attach a spectroscope. They didn't know how they were going to do this, but they were going to attach a spectroscope to a telescope. Now, here you get some idea of how they kind of did that. Here's the spectroscope down here at the observing end of Huggins's telescope. And here you have a lot of batteries, and these are the spark spectra that they used as comparisons. And Huggins says here it was then that an observatory became a chemical laboratory, essentially. Now, when this exactly happened, it would be very nice to know this. We don't know exactly when that first fine night was that they set out to do their observations, because if we look at Huggins's notebook, we find, unfortunately, he did not make any entries in his notebook from March of 1860 until July of 1862. So all that time is just not anything that we have any information about. And when he does go back to making notes, this is what he's talking about. This does not look like spectroscopic information. I don't know if you can tell what this is. What does it look like? Jupiter. Well, it's not Jupiter. No, it's not.
Red spot?
Nope. That is a shadow of a transit of a moon's shadow. It is Saturn. Now, why would Saturn look like this? That's right. And why do you think Huggins is looking at Saturn so intently when he's, really heft up on using his spectroscope and stuff like that, starting out? He wants to find some new moons. The last time that Saturn had been edge on. New moons of Saturn had been discovered, and there was nothing quite like having your name attached in all history books to discoveries of planetary objects. And so you see, here's one thing, he's looking very carefully at all these little moons orbiting around Saturn, looking out, and he and just about every amateur astronomer worth his salt was doing exactly the same thing. Now, we know that they eventually got going on this project because, fortunately, I guess, there's always that little urgency of competition. You have Giovanni Battista Donati in Italy, and you have Lewis Morris Rutherford in the United States. He lived in Manhattan, actually, and he was actually an observer in Manhattan in the early in the middle of the 19th century. You could get away with that sort of thing. But they were beginning to publish their own observations. They had also heard about Kirchhoff's work and were getting enthused about working on this, as was another Italian astronomer, Father Angelo Secchi, who was an observer at the Vatican Observatory. And so there was competition for priority on these things, and Miller and Huggins very soon published their own paper in 1863 on their work, and embellished theirs quite a bit, made very detailed diagrams of the spectra of the stars. Now, if that was all that Huggins had done, if he, like Donati, like Secchi, for example, had just worked on starlight, had just examined star spectra, that would be pretty much the end of the story of his involvement in this effort. But Huggins was a businessman first. He kind of disparaged that idea that he wasn't an academic, he wasn't somebody who had gone to Cambridge and so on, that he had just been a silk merchant. But in fact, that actually played a very important role in his whole method of operation. He was an opportunist. He was eclectic. He was looking for anything that would bring him some kind of acclaim, some sort of discovery, and he was willing to try a lot of different things. And so one of the things that he began to examine that no one else never even crossed their minds to do was to look at nebulae. Now, at that time, we think about dark matter today, we think about dark energy and these very mysterious kinds of things that astronomers are all in a quandary about. We need better instruments, we need better ways of doing our observations. Well, that's the same kind of status that nebulae, the question about nebulae, was in the middle of the 19th century. This fellow here, William Parsons, had built this telescope in Ireland, not exactly the best place if you're going to try observing nightly. This telescope was 6 feet in diameter. This is a person right down here. Here's a little person. Here's another little person. And there's actually a man standing up here. So this was an enormous, it was the largest telescope in the world. And it was built largely by Parsons in order to pursue this question of what nebulae actually were. And the idea was that, so they're fuzzy. A lot of them are fuzzy, but if you get a slightly bigger telescope, a lot of these things resolve into little stars. And if you just had a bigger and bigger and bigger telescope, you would resolve them all into stars eventually. Well, Parsons found that that wasn't the case. And he languished over this idea that we would never, ever really be able to know what nebulae were. Norman Lockyer, who was an amateur astronomer as well, he was the founder of Nature, the journal Nature, actually, a few years after this. He wrote an article in a popular magazine asking, what are nebulae, since they certainly are not what our textbooks describe them. The genius about Huggins was thinking that maybe, telescopes, this is what we've always thought were going to be the way of answering our questions about things in the sky. Maybe the spectroscope, just like it taught us stuff about the stars, maybe it will teach us things about the nebulae. And so he decided to tackle this problem. We don't know from his again, we find his notebooks are a little bit lacking. That whole August 1864, he's got March in 1864, and then the next entry is July of 1865. So in August of 1864, when he made his very first observation of the nebulae, we don't have an observatory notebook record of this. All we have are his published accounts. And he tells us that he first tackled a planetary nebula. Some of you may be familiar with this one called we now call it the cat's eye. That's a very recent nickname for it, but this is what Hubble tells us it looks like. This is what you'll see if you have a reasonably large telescope. So it is a bluish color, and I think that its bluish color was what attracted Huggins to it, because he thought that the color might give some clue. There would be some color in the spectrum to give a clue to what it was like. So in 1897, in his retrospective essay, he writes, "After a few moments of hesitation, I put my eye to the spectroscope. Was I not about to look into a secret place of creation?" You can just imagine carrying the reader along, just kind of on the edge of their seat. What was he going to see? Well, in this little circle below here is a photograph, a modern photograph, taken a year ago on the anniversary, the 150th anniversary of Huggins's observation, and you see what it was that he saw. He actually didn't see even as good as that. He only saw one line. He thought he was going to be able to see a continuous spectrum with some dark lines going through it. That was what he really thought. He thought that nebulae probably can't be too different from stars. They just might look a little fuzzier or have different lines, different dark lines crossing it. And he thought that's what he would be seeing. But instead, he saw one bright line. And when he compared it with other elements unknown on Earth, the closest he could come was nitrogen. Now, he realized soon after that it wasn't really quite lined up with the nitrogen line. It was a little off. And what he concluded from that was that maybe what we have here is not only a very peculiar thing that has these very specific lines, just like it's made out of one element alone, but we have something that is made up of an element that does not exist, that's not known to humans. And he nicknamed it nebulum for a while. It wasn't until the 20th century that we discovered that it is actually a doubly ionized oxygen line. But it was a complete mystery. But it prompted people to begin looking, and Huggins to look at many more of nebulas. Here's some other of the planetary nebulas that he looked at. And he began to recognize that there was more than just one line. He saw actually three lines in that blue area of the spectrum that were really very bright and very noticeable. And he tried very hard to figure out what those things were. His conclusion was that nebulas are just different. They're not really like stars. Now, he was going to change that view over the course of time, and of course astronomers have developed many more ideas about the reality of what nebulae are like. But in 1865, Huggins concluded that he had found something really quite new in the heavens, and it prompted him to look at some other things. And he was very lucky in 1866 to see a nova. In fact, as soon as he got word that there was a new star in the sky, it was the first thing he did was train his spectroscope on this object, and he was startled because what he saw was not something that looked like a star either. It was kind of like a star in that it had dark lines, but it also had, I don't know if you can see that, but there are bright lines as well. And he thought that what he was witnessing really was some kind of cataclysmic explosion in a star-like object. There were some variable stars that had signatures like that had some bright lines in them that some astronomers had started to notice. And Huggins suggested that perhaps it would be worthwhile looking at these in advance of their explosion. Maybe we could begin to predict when a star was going to explode. He also tried to measure the heat of stars. This was a totally unsuccessful adventure for him. He had detailed descriptions of his work in his notebook, but he hardly published anything about it because it just wasn't something that worked out very well for him, and he found it to be more of a dead end. And these things are very interesting to me as a historian because it shows this very fertile mind, willing to try things even when things were quite risky. And he knew when to sort of fish or to cut bait and move on to something more useful. And one of those more useful things is probably the beginning of his most important contribution to the history of astronomy and to the practice of modern astronomy, and that is the study of motion in the line of sight. Back in 1864, he drew this very wonderful spectral diagram of the two components of alberio. Is there anybody who hasn't seen alberio in a telescope? Take a look tonight. Well, not tonight. Okay, the next clear night, take a look. It's right in the middle of the summer triangle. It's really right overhead all evening. It's a beautiful, beautiful double star. Gorgeous contrast between blue and orange, and that's what attracted attention to it by a lot of astronomers trying to figure out what. This obviously color in stars was not just a figment of our imagination. It was real. What causes the difference? Well, Huggins began to argue, and this picture is intended to show it, that actually there's a chemical difference between the two stars. And he's wrong, of course, but that was his guess because you see how the lines of the two stars, the spectral lines, are quite different and indicate that there must be something chemically quite different about the two. Well, in discussing this at the Royal Society at that time, it just so happened that James Clerk Maxwell was in the group that was discussing this. And one of the things that had been proposed was by Doppler himself. Doppler thought that binary stars have different colors because one of them is coming towards you and one of them is going away from you. And they're traveling at very great speeds, and so just like pitch changes audibly when something is coming towards you and going away, well, that's what's happening with double stars as well. They're maybe orbiting and moving one away and one towards you. Well, Maxwell said, stars can't be moving towards and away from us because if that was the case, why, you would see a shift in their spectral lines compared to terrestrial lines. This was in 1864 that Maxwell was talking about this. It must have planted a seed of a possible mode of progress and procedures that Huggins was going to take up a little bit later, but he didn't have good enough spectroscopic equipment to detect the very tiny, tiny differences that he imagined would be observable in the spectra of a star. But this was the first mention of this kind of idea of actually comparing terrestrial elements and their spectra with the spectra of a star to see if there is any sign of any motion. A few years later, though, Maxwell was one of the first people that Huggins wrote to ask him a little bit more about this whole idea of shifting spectral lines. By now, he had gotten himself a much better spectroscope, one that he thought would be able to detect these very tiny differences. And so in February of 1868, he begins to look at the star Sirius, comparing its light, the spectral signature of Sirius, with a spectrum of some hydrogen that he has glowing in his observatory. And what he sees indicates to him that, even though it's very tiny, very, very hardly noticeable, that in fact Sirius must be moving a little bit towards us. He's doing this, by the way, completely with his eye. He wasn't taking photographs. He was, just trying to gauge the slight shift using his eye. A few weeks later, he looks again. Maybe it's moving away from us a little bit. The next time he looks, about a week or so later, yeah, definitely, it's moving away from us. 2 days later, no, wait a minute, it's moving towards us. Now, in the end, when he finally published his paper in May of 1868, he concluded that, in fact, it was moving away from us at about 29 miles per second. He's way off, okay. But he managed to convince his colleagues that this actually was something that was possible. Possible to observe, possible to do, and meaningful. Useful not to just people who are trying to guess what, wondering what stars are made out of, but useful for people who want to map the heavens. Because now you not only get the stars and their positions this way, but you get some sense of the 3D-ness of it. Stars moving towards you and away from you, if you could just get really accurate measures. Now, it took a while. He was very excited, of course, by the 1890s. Many people were using this method and using it quite effectively. Looking back on it, he said, people were just a little reluctant to use it at first, but it really is a very important thing. They were reluctant to use it for a lot of reasons. George Airy was one. George Airy was the astronomer royal, and his job was he was an employee of the Crown, and his job was to assist navigators in their navigation. And so he writes to George Stokes and says, this is in 1872, in some of the German pamphlets now afloat on optical subjects, there is repeated allusion to das Doppelprinzip, or some such term conveying the idea that a man named Doppel has introduced some optical principle. He wants to know more about this thing. What's interesting about this letter to Stokes in 1872 is that back in 1868, when Huggins first published his paper, Airy was one of the people that had been asked to review that paper. Airy knew all about Huggins. He had just forgotten about it. He didn't understand it. He didn't quite get the drift of it initially. And so now he's going to be reminded of it, because Stokes immediately writes back and he says, well, to answer your question, you might look at this paper that was written a few years ago. Stokes was courteous enough not to say that you reviewed yourself. And you can find all the answers to your questions there. But here's another reason why it didn't catch on too quickly, and you can see what kind of results people were getting. These first sets of results were all done by eye. Vogel is the very first to try to use photography, and now you see that there is getting to be some consistency in the measures. Here's what our modern estimate is. So Sirius is actually approaching us at about 5 miles per second. All of this work on the nebulae, on the motion in line of sight, came to the attention of one of the most prominent astronomers in the British Isles, the Reverend Thomas Romney Robinson, who for decades had been the director of the Armagh Observatory. He had a lot of clout. A lot of clout. And he decided that Huggins was exactly the kind of person that we need to have working on this much more seriously with much better equipment. And so he proposed to the Royal Society that the Royal Society itself pay to have a new and fine instrument built for Huggins's personal use in his house. It wasn't like they were going to build it and give it to Greenwich Observatory, and Huggins would have to travel to Greenwich every day to use it. It was going to reside in Huggins's own home, and he was going to be free to use it for as long as he could make use of it. This instrument was going to cost more than £2,000 to build, and somehow Robinson managed to convey enough enthusiasm for this project that the Royal Society agreed to do this. Now, this was a great, if somebody agreed to give you a telescope like this for your own personal use in your own personal private observatory, you'd jump up and down, I'm sure. No one would refuse that. The only problem for Huggins was that it meant that he was really going to have to use it. He was going to have to use it seriously, and it wasn't going to be just like this amateur business, like, oh, well, I just don't feel up to it tonight. He was going to have to actually make use of it. A complication arose in that just before the telescope was finished being built, his colleague, William Allen Miller, died unexpectedly of a stroke. So now he was on his own. His neighbor was gone, his helper, the one that he could always count on to come in and assist him. He wasn't a wealthy man. He couldn't afford to pay somebody to come and assist him every night with this work. And he started having problems, too, because one night he went off to get a book that he had left in the house. I mean, the house and the observatory are attached, not a big distance. He came back to find that a lamp had knocked over and started a small fire. He sprained his ankle and couldn't work for a few weeks, and he felt very guilty about not being able to. So how is he going to solve this problem? Not being able to afford an assistant, but needing someone to help him out. Well, if you're a 50-plus bachelor and your mom has just died, isn't there to darn your socks anymore, right? And you need an assistant in the observatory, and you don't want to pay her. You find a wealthy woman who can be your helpmate for the rest of your life. And in fact, this was such a wonderful union. Margaret Huggins was born in Dublin. How the two exactly met is not entirely clear, but she had been interested in astronomy from her early childhood, presumably because she had read an article that she claims was written by William Huggins when she was a girl. She was some 24 years younger than he. And so when she was a young girl, she claims that she had read an article on astronomy written by Huggins in this magazine. I have looked through every issue of this magazine, have found no articles written by William Huggins, so that's an apocryphal story, but it sure is romantic to think that then she grew up to marry the man who had interested her in astronomy in the first place. But she immediately set to work, right after they were married, and she described herself as being his able assistant. You know, she kind of dusted and tidied things up, but she was actually a full-fledged full collaborator. She began keeping the notebooks, for one thing. She was also a photographer. Recall that Huggins had not really used photography up until this point. And her very first entries in the notebook are about how to use photography with, to photograph the spectra. She designed a camera that would be able to arrange the plates so that all of the colors in the spectrum would be in focus when the photograph was taken. And she shaped the direction that the observatory program went on after they were married. In fact, here's a statement by hers. When this photograph was one of the most phenomenal photographs ever made at towards the end of the 19th century. It was by another amateur astronomer, Isaac Roberts. People, including Huggins, when they saw this photograph of the Andromeda nebula, as it was called then, because they didn't know really what it was that this was proof of the nebular hypothesis. This was a solar system. There was no question. Look at these planets. You can see the planets right there in formation in the structure of this photograph. Well, Margaret's claim was that, okay, Roberts has photographed this nebula. He's captured its body, but if we can get the spectrum, if we can photograph the spectrum, then we will actually be able to capture its soul as well. And so that was one thing that she and William went to work on. And this was partly because of a really great, rousing controversy. This was a tooth and nail controversy that was going on at the time about what actually celestial bodies are mostly made out of. Norman Lockyer, the founder of Nature, was convinced from his study of nebulae and meteorites and comets and so on that the root of everything was magnesium. And in particular, he found that most of these objects had the elements that were found in meteorites. And so he imagined that everything that you could see in the sky, whether it was a star, a comet, a nebula, was just a swarm of meteorites. Some of them were really densely, swarming very densely. Some of them were swarming very loosely. But that was his view, that this nebular line that Huggins had argued was maybe nebulium or possibly nitrogen was in fact magnesium, related to magnesium, and was found commonly in meteorites. Huggins said, no, 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 no. Here, I looked at this very, very carefully with my extremely fine equipment courtesy of the Royal Society, and I can see that these lines do not coincide at all. Now, one of the things you'll notice in this slide that is up here, this was published in the Proceedings of the Royal Society. 2 authors, William Huggins and Margaret Huggins. This is the very first paper in which she appears as co-author. They've been married for almost 15 years. They've been working together very closely for all this time. This is the first paper that he decided to include her as co-author. Now, there are a lot of reasons why he might have done this. Maybe he's, it's about time. She's finally figured out how to help me out. Well, she had figured that out a long time ago. I have a sneaking suspicion that there was something a little bit more to it than that. For one thing, in the observatory notebooks, not in the paper, Margaret notes that just before they're about to publish their paper, she discovers that the telescope and the standard source that they're using for the magnesium light is out of alignment. They've made all their measures based on this set of equipment that they thought they had in alignment, but actually is just a little out of alignment. William at first disagrees. He's very resistant to accepting this. Finally, he recognizes that, in fact, this is a problem. And what are they going to do? The nebula that they're looking at is Orion, the Orion Nebula. And this is in the spring. They've done all of their work now. Orion Nebula is not going to be around for much longer in the sky, and they can't be guaranteed any additional time to observe it. So they decide that time is of the essence. We've got to get this paper into a print. And so I don't know whether Margaret came up with this idea or it was just because she had alerted him to the possible problem and they collaborated to come up with this wonderful idea. But they claimed in their paper, to prevent any possible error in the observation of apparent want of coincidence of the nebular line, the arrangement was purposely made that the lines of magnesium were seen to fall a very little on the more refrangible side of the middle of those lines. In other words, that misalignment, we did it on purpose. And we did it on purpose so as to give our opponent, i.e. Norman Lockyer, every conceivable advantage. But you see, even with this advantage that we've tried to give him, it still shows that we were right after all. So kudos to Margaret for noticing this misalignment in advance. It would have been very embarrassing because Norman Lockyer would have discovered the problem, I'm sure, and made a big stink out of it because that was what he liked to do. But she saved his skin on that one and came up with a very good way of wiggling out of it. In 1900, William Huggins, an amateur, no university degree, no proper formal education, was elected president of the Royal Society of London. Now, you can imagine a person with no even rudimentary elementary education, an amateur astronomer today becoming president of the National Academy of Sciences. It is really quite a phenomenal thing. He served a 5-year term. And while he was president in 1903, London was visited by the Curies, Pierre and Marie Curie, to talk about their new discovery of radium. And the Curies saw to it that the Hugginses got a sample of radium to do some spectroscopic work. Their work was not just on astronomical subjects. And they conducted work. They didn't examine the spark spectrum of radium. Others were doing that. What they were interested in was trying to capture the natural glow of radium. They had to take very long photographs. This was a very unsuccessful venture for them because it turns out that all they got was nitrogen lines. Mainly, they got the excitation that the radium was giving to the surrounding atmosphere. But no one knew No one had any clue as to what was causing this glow, and no one had any clue as to what made radioactivity actually function in those days. And so many different avenues of research were tried. This was one of them, and one of the less successful ones, but it was really quite an ingenious plan that they had. After William died, I just want to say a few words about Margaret. After William died, she did quite a bit to protect his reputation. Not protect it so much, but advance this historical legacy of her husband. Now, I mentioned that she described herself as his able assistant, that she just sort of dusted the furniture and stuff like that. This was a very interesting thing that puzzled me a great deal until I realized that in Victorian England at that time, one of the things that was the sign of a proper lady was that you elevated the role of your husband in society and you withdrew, you kind of wrapped yourself in this invisible cloak. You might have been the wheel and the engine and the fuel and stuff going on in the background, but you never advanced yourself to the detriment of your husband's reputation. And Margaret worked very, very hard. After her husband died, she read every single obituary that was written. And she had critical comments. This is a letter that she wrote. This was not a letter to somebody. This was a model letter that she felt that Professor Newell should write to apologize, not only apologize, but withdraw many of the false statements that he had made in this obituary of her husband in a popular magazine. You know, not in a scientific journal so much, but in a popular magazine. For her, this was the worst thing that could happen because it's like a Pandora's box. Once false information gets out, there's no pulling it back. And she felt that it was beholden to Professor Newell to make this retraction, make it very, very soundly. She contributed some of the instruments that the Hugginses had collected over the years to Wellesley College. In fact, she made a tremendous gift to Wellesley College before she died. She gave all of the observatory notebooks to Wellesley College. It's in Boston, Massachusetts, or just outside Boston, Massachusetts. The Hugginses never came to the United States. She had no connection with Wellesley, except that the director of the observatory at Wellesley, which was a new college at the time, this young woman came to visit the Hugginses and to try to learn from them what she should be teaching her students in order to prepare them to be modern astronomers. Margaret was very impressed with this because she thought this was a remarkable thing, that young women were going to get the kind of education she never had, and they were going to come out and be prepared to be professional astronomers. But anyway, she gave them, the astrolabe is obviously not a modern instrument, but it was part of their collection of old instruments that she gave to the college. And she gave there were actually 3 stained glass windows that had hung in their house. My favorite is the one on the right of the sun with the Fraunhofer lines. And what you see here is this is supposed to be a nebula here. And there's the nebular spectrum. And this little thing peeking out here and extending up towards the sun is Halley's Comet, which appeared just about the time that William Huggins died. It's very beautiful, and actually, do you recognize what this is from? This is from the Bayeux Tapestry. This is the men standing there, and they're pointing up to this object in the sky that's on the edge of the tapestry, and it is actually Halley's Comet that has appeared and foretold the death and the defeat of the English king who had lied about his status and so deserved to die. This was, of course, made in France. So that's their side of the story. Margaret designed the brass grillwork for the little niche that their ashes are kept in Golders Green Crematorium and Cemetery in London. And so you see there's William's casket down here is a little thing holds his ashes, and hers is up on top. And she had it inscribed with a verse from Psalms, which is very artistic. But here's an example of this Victorian view that Margaret and William both held to, Margaret particularly. The man is eminently the doer, the creator, the discoverer, the defender. His intellect is for speculation and invention. The woman's intellect is not for invention or creation, but for sweet ordering, arrangement, and decisions. So that dusting up in the observatory, that was what she felt she should let herself be known for. Now, I'll close just with this one little bit about William and his life as a silk merchant that sort of set the stage for that kind of crazy, eclectic work pattern that he had, where he would just flip from one object to another. He never was one of those who would do a whole catalog of all the stars and their spectra. He wanted to make discoveries in a variety of ways, and he was willing to take a lot of risks. And whenever he made a discovery, he had a way of presenting his discovery in print, writing up his work. It was very persuasive, very enthusiastic. It was almost as though he was treating it like an exotic bolt of cloth and trying to sell it to his colleagues. And he was very effective at this. When he made mistakes, he was very quick to try to point out and correct them. He never withdrew from any kind of opportunity to point out his own mistakes. In fact, one of his views was, it's better for me to point out my mistakes than to have it brought to everybody's attention by someone else. And he wanted control over his legacy, over the story that people would live to tell about his contributions. And hence that wonderful essay that he wrote in 1897, which has withstood the test of time, is one of those examples of where he's going to write the history himself and hope that everyone will adhere to it. And by and large, everyone has. Now, I will say that this has some differences. I have quite a few differences with William's portrayal of himself and his work in my rendition of his, but this is based on his letters, his unpublished work, his entries in his notebooks and so on, stuff that he never intended for people to read. But one of the cool things about being a historian is that when you've got people with mail, you get to read it, and they're dead, so they can't do anything about it. But you learn so much more about the complexity and the variety of choices that these individuals were confronted with. You marvel at their ability and their agility to make decisions that worked out as well as they did. This is his correspondence, these two volumes here. If any of you would like to take a look at them, you're welcome to take a look at those. This is what this book is based on, but because it required going to so many different libraries and looking for all these different collections of letters in so many different places, I thought it would be useful for researchers to have it all in one place that they could just easily refer to. But anyway, thank you very much. I hope this has not been too long.
Minute for questions.
Yes.